Welcome to this explainer. If you've ever stared down a massive 500-page JunOS technical manual and just thought, okay, how do I actually extract exactly what I need to build a practical, secure network architecture? Well, you're definitely in the right place. Today, we're going to act as your structural guides. We'll be translating all that dense documentation into a crystal clear, actionable blueprint for configuring IKE and IPsec right on your JunOS devices. Let's get into it. So how exactly do you build a secure, impenetrable tunnel across the wildly unpredictable public internet? Well, let's think about it using a construction metaphor. You really have to look at two distinct phases of building. Think of IKE, or Internet Key Exchange, as the delicate negotiation of our blueprints and security clearances, getting all the permits in order. IPsec, on the other hand, that represents the actual steel, concrete, and pavement of our secure tunnel. That's where the data traffic is actually going to flow. To get there, here's our game plan. We'll start with the IKE and IPsec foundation, then move into prepping your JunOS device. After that, we hit Phase 1 IKE configuration, Phase 2 IPsec configuration, dive into certificate-based authentication, and finally, we'll bring the whole shebang together. All right, let's kick things off with Section 1, the IKE and IPsec foundation. Before we start configuring anything, we really have to know our materials, right? The absolute crucial point here is distinguishing between our two main protocols. So IKE handles the secure handshake, the key management, and that initial tunnel negotiation. Basically, it's the diplomats talking things out. IPsec is the protocol suite responsible for the actual data encryption. It does the heavy lifting, protecting your data packets as they physically transit the network. When you look at the topology we're building, we are bridging an untrust zone, think the public internet or external nodes, to a highly secure trust zone. Right there in the center, acting as our fortified checkpoint, is a Juniper SRX series chassis cluster. Literally everything we configure today is designed to securely route traffic across these exact boundaries. Now, what's really interesting here is the strict nature of modern protocols. The JunOS guide explicitly highlights the difference between IKE version 1 and version 2. If you configure a peer as IKv2, it flat out refuses to fall back to the older, less secure IKv1, even if the remote peer begs for it. So to enforce this high standard on our devices, we actually have to explicitly set our version using the v2 only command. No compromises. Moving right along to Section 2, prepping your JunOS device. You obviously can't build an IKE tunnel if your router doesn't have the tools installed. So first things first, you've got to ensure you have the JunOS IKE package actively installed on your device. You can verify this super easily with a quick show version match command. Missing it? Just install the JunOS IKE.tgz package. And lastly, you really need to know how to bounce the critical processes. Restarting ikemd handles your configuration management, while restarting iked resets your key management right on the routing engine. Let's take a quick, kind of surprising detour, straight from the manual's legal pages. Right there in the year 2000 notice, Juniper assures us our hardware is Y2K compliant, stating your IPsec tunnels will easily survive time-related bugs through 2038. But you've got to keep a close eye out for that quirky 2036 limitation with the network time protocol. It's just a fascinating little reminder that our network infrastructure is deeply, literally tied to the ticking clock of our systems. All right, site prepped. Section 3, Phase 1 ICK configuration. Let's start building. The JunOS configuration hierarchy is just wonderfully logical, and it requires a strict 3-step workflow for Phase 1. First up, we define the security proposal. This is where we're choosing our cryptographic algorithms. Second, we bind that proposal to an IKE policy. And third, we attach that policy to our external-facing IKE gateway. Let's break down exactly how this syntax looks. Looking at the CLI syntax, this is where we establish our initial blueprint. Under the edit hierarchy, we're setting our IK proposal. Let's name it IKEprop. We are strictly enforcing highly secure encryption algorithms here. Specifically, we're using AES-256 CBC for encryption, SHA-256 for authentication, along with Diffie-Hellman Group 2 for the key exchange. This is absolutely a robust, modern cryptographic standard. So now that the proposal exists, we just reference it. By executing the command to set the security IKE policy with our proposal, we are directly binding our newly created, highly secure proposal right into our active IKE policy. If you want to think about it visually, the policy is essentially the folder holding all of your approved architectural plans. Finally, for Phase 1, we attach this folder, this policy, to our gateway, which is the actual door to the outside world. And remember that super strict standard we discussed a minute ago? This is exactly where we apply it. Under the gateway configuration, we strictly enforce the version v2 only parameter. That keeps our negotiation standards rigid and outright rejects any outdated legacy connections. Blueprints approved. Let's move to Section 4, Phase 2 IPsec configuration. Phase 2 workflow actually perfectly mirrors Phase 1. We create an IPsec proposal where we define the encapsulating security payload, or ESP protocol. Then we build the IPsec policy. But what is truly brilliant here is how we enforce perfect forward secrecy. By setting our PFS keys, we guarantee that even if a future key is somehow compromised, all past traffic remains perfectly safe. It makes our roadway virtually impenetrable. After that, we just bind it to our VPN in the gateway. Now for Section 5, certificate-based authentication. If we really want to elevate our security, think going from a standard lock to an advanced biometric scanner, we need to step away from pre-shared keys entirely. Look, a simple pre-shared key is essentially just a complex password, and passwords can be compromised. By setting the authentication method in our IKE proposal to RSA signatures, we're instructing JunOS to utilize robust RSA, or ECDSA if you prefer, digital signatures for peer authentication. Now the devices verify each other using complex cryptography. Of course, once you demand RSA signatures, your router actually needs to know which digital ID card to show at the door, right? You have to explicitly point your IKE policy to your local certificate identifier. We can set the local certificate to a pre-enrolled certificate named Spoke, for example. This tells the router precisely which cryptographic identity it needs to present to the remote peer. And to ensure absolutely zero trust errors, we've got to complete the authentication circle. Not only do we present our ID, but we must dictate whose IDs we're willing to accept. By defining the trusted CA profile, we definitively trust our specific root certificate authority. If a remote peer tries to connect with a certificate that wasn't signed by this exact CA, the connection is instantly dropped, no questions asked. We have all the pieces. Let's hit Section 6, bringing it all together. It's awesome seeing how all these moving pieces snap together. Your Phase 1 IKE gateway and your Phase 2 IPsec policy don't just float around in the void. They must be logically bound directly to your secure tunnel interface. In JunOS, this is typically your ST0 virtual interface. Once they're bound, you just place that ST0 interface into a security zone like VPN and write your routing policies to allow traffic to flow safely from the VPN straight to your trust zone. But wait, once you hit commit, your work isn't quite done. You always need to verify the bridge is actually holding weight. Make sure to run the essential operational commands. Checking your IKE and IPsec security associations will quickly confirm if the tunnels are actively up and negotiating. Viewing your PKI profiles ensures your certificates are valid. And checking that ST0 interface proves your brand new bridge is safely carrying active data traffic. So we've successfully built an incredibly secure JunOS tunnel today, leveraging high-end suites like AES 256 and strict certificate verification. But seeing how deeply we rely on these mathematical algorithms leaves us with one massive question to ponder for the future of network security. As we lock down our infrastructure today, how will the looming, inevitable rise of quantum computing force the complete next evolution of these very cryptographic suites we just deployed? Definitely something for all of us to think about as we design the networks of tomorrow. Thanks so much for joining me on this explainer. I'll see you next time.